In my last video, we looked at probabilities of events occurring in sequence when there are only two events, and we say that these events are independent of one another. That is, the probability that, say, an event A and then an event B occur in sequence where the likelihood of A happening and it actually happening does not affect the likelihood of B happening. But what we discovered was essentially this. The probability of two independent events, we could just say the probability of A and B can be rewritten as the probability of the first event times the probability of the second event. So for all intents and purposes, you could interpret this word "and" here as kind of meaning multiply when we're discussing things that happen in sequence. What I want to do in this video is extend this concept to three or more events occurring in sequence so long as they're independent of one another. So this multiplication rule is what we call it here, probability multiplication rule number one. We say it can be extended to include three or more events that occur in sequence. This formula would just look like this instead. So if we're saying that A happens, we want to find the probability that A happens, then B happens, then C happens, and so on and so forth out to the K, the event K. We could just go ahead and replace all of these instances of "and" with multiplying, and we could say we'll just write these as simple probabilities. And what this does is it actually makes our job a whole lot easier. Instead of having to list the sample space, we could just go find the probability of each of these simple probabilities or simple events, and then we could just multiply them together. So what I'm going to go through here are a few examples of problems you'll see like this quite often. Starting with this one here, it says a poll found that, say 46% of Americans say that they suffer great stress at least once a week. So my question is this: if three people are selected at random, find the probability that all three say that they suffer great stress at least once a week. The thing here is this: people fail to see that when I say, well, find the probability that if you grab three people that they're going to be stressed out at least once a week. The idea is this: when you talk about grabbing three people, we're talking about, first of all, something where we would probably grab one person, and I'll say that S stands for stress. But you're going to grab one person, and then you're going to grab another person from the population, and then you're going to grab a third person from the population. So what we need to do is we need to start by interpreting this as kind of meaning that these three stressed out people, we grab them in sequence, okay? And then the other thing is this: it's not so much important whether or not we released the first person back into the population unless you have a very small population. So according to this poll, we're saying about 46% of Americans, in the entire population, which is so large that by kind of maybe holding on to this person right here and not releasing them back into the population might not affect these other two probabilities very greatly, not significantly enough that you'd notice it. So we're going to go ahead and interpret this as a situation where grabbing three people is three people in sequence, and that the population is so large that these events could be considered, for all intents and purposes, independent of one another. So what we are told right off the bat is this: we say the probability that somebody's stressed out in the first place is 46%. So we could say 0.46 is what we were given here. If we want to find the probability then that all three people are stressed out, well, writing out this probability, we say, well, according to the multiplication rule, we could just say, well, it's the probability of one stressed out person times the probability of the second stressed out person times the probability of the third. And so now what we'll do is we'll just say, well, 0.46 times 0.46 times 0.46. Honestly, if we wanted to do these things in a row in sequence where they're independent, you can start to see how we could just take the probability of it occurring once and then take it to the nth power, where n would be the number of times that we see this event occurring in sequence. Here we say 3 times. So we say 0.46 to the third power, and it's not going to be a very good chance, I don't think. It's less than a half each time. But 0.46, and I'm going to say cubed, we get 0.097336. So approximately, equal to 0.097336. So we're going to write this both as a decimal and as a percentage. So we say about a 9.7336% chance that you'll grab three consecutive stressors, three stressed out people. Okay. So another example you're going to see here is this. I mean, not that it's going to be free throws, but you see these a lot in probability classes. So I use an example. I had to go look this up. I'm not a big basketball fan, but LeBron James, this is one of the best, professional basketball players, arguably, that's ever played. Has a career free throw percentage of approximately 75%. So we're going to round it off to 75, which is a good number, but that's pretty good. That's 3 out of every 4 baskets, he's projected to make it at the free throw line. So what I want to know is this: determine the likelihood, and when we see likelihood, we're thinking probability, but determine the probability that Mr. James, shooting 10 free throws, is going to make all 10 of them. Okay. So the key thing here is this: he's going to shoot 10 in a row, and we want to find the probability that he makes all 10. So when we write this out, what we're going to say is this: we're going to say probability makes all 10. Now, if we're going to say M represents makes, the idea here is this. We're going to say, well, we already have been told the probability that he makes one of them is 75%. So using this information, how could we find the probability that he makes all 10? The idea here is that I don't want to have to write probability of makes, and then he makes another one, and then he makes another one, and what we're saying here is this dot, 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 makes, whoops, not an A, an M. But there would be essentially 10 of these factors right here, 10 factors of making it. So what we're going to do is we're going to say, well, making all 10, that would really be the probability that he makes one times itself 10 times. And the fact that he makes the first basket does not affect him making the next basket here. These are independent events. So again, we're going to say, well, really what this comes down to being then is if he makes one as, a 75% chance, really what's the probability that he makes all 10? So it's really going to be 0.07 or 0.75 to the 10th. We get 0.75. We're going to say to the power of here, 10. And, oops, I think that I need to use a different to the power of button here. Second. Where is it hiding? Power 10. Well, we could say 0.75 to the power of 10. I'll try this again here. There we go. That's better. I must have had a value already in there. But about a 0.05631. So to the 10th power, 0.05631. And as a percentage, of course, this would be a 5.631% of the time. That's really good to say, well, how likely is it that he makes 10 in a row? That's like 5 out of every 100 times, or 1 out of every 20 times he repeats this experiment. So just to show you, kind of how bad somebody else is, we'll do my statistics down here. But essentially, this is the likelihood that he makes 10 in a row. And we could just say likelihood that he makes 1 times, itself 10 times would be that to the 10th power. So I say as a follow-up, find the probability that he makes 9 or less of the 10 free throws. So now this is an interesting situation. Notice I use the word or here. If you've been studying probabilities at all, you say that two mutually exclusive events with, an or in between them, this is our addition rule here. We say or, kind of translates to adding these together. And so when I say makes 9 or less, I'm going to kind of write out a few of these here, but this means makes 9 or 8 or 7 or 6 or, or 1. All the way down to this. Which would mean we would have to go find the probability that he makes 9 out of 10, and then add that to the probability that he makes 8, plus the probability that he makes 7, plus the probability that he makes 6, and so on and so forth here, all the way down to this probability that he makes 1. We would have to get these all individually and then add them together, or what we could say is essentially this. If we were to say, well, thinking about this, the probability that he makes 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10, if you were to add them all together, they would add up to 100% of the probable things that could happen. So when we say 9 or less, what we're instead going to do is we're going to rewrite this as probability that he doesn't make 10, not all 10. And the reason why we want to do this, actually not probability that he doesn't make all 10, but 1.00 minus the probability that he makes all 10, is because what we're really saying is let's take 100% of our stuff, this 1.00, and we'll subtract off the probability that he does make all 10. And what should this do? Well, it should leave behind the likelihood, 0.05631. It should leave behind all of these other likelihoods right here. So again, we're saying if I were to say add this probability of 10 in here, we would get 100% of the likely things that could happen. So what we're doing is we're taking 100% of the stuff and we're subtracting off the probability that he makes all 10, and it's going to leave behind all these other probabilities right here. So again, with our calculator, I'm going to go ahead and subtract 1 from this and then call it positive. But the likelihood that he doesn't make all 10, that he misses at least one of them, is a 0.9437-ish kind of thing. So 0.9437, or a 94.37% of the time, theoretically, he should miss at least one basket, which is reasonable. I mean, you're likely to miss at least 1 out of 10. Okay. So now as a final part of this problem, I say, well, let's consider that my free throw percentage is about 20%, and I'm telling you, that's me being nice to myself, okay? So we say the probability that I make it, Mr. A makes it, is 20%. So my question is this: how likely is it that I make 10 free throws in a row? So we say probability makes all 10. And we'll just say that it's the probability that I make it once times itself 10 times And so getting our calculator out here, I'm not even going to write this one down. I'll just show you. But we say 0.2 to the power of 10. Now, moving this decimal twice to the right, that is a 0.0000124% chance. Okay, so it's only going to happen once out of every 1, 2, 3, 4. Let's see, 100, 1,000, 10,000, 100,000, million. It's like a 1 in a million shot. Okay, so it's not going to happen a lot of the time. And so again, it's this 1 in 5 times itself 10 times, this 1 over 5 to the 10th kind of idea. I just converted my decimal to a fraction here, but it's not good, people. It's not good. There's a strong likelihood that I'll miss at least one. But that's how you do this with 3 or more events. Cheers.